Hello, Honors Chemistry, and welcome to Chapter 5, where we talk about compounds and how to name them. Like it says in your outline, this does tend to be a challenging chapter for many people. Not because the material is any harder than any other chapter, right? Like, this is not harder than learning those conversion factors that we did in Chapter 2, right? But if you'll think back to Chapter 2, right, at the very beginning, there's a strong possibility you thought, oh my gosh, this is so hard, until you did, right, lots of practice. And this will be the same thing, right? Because here we are layering on so many levels, right? We've got the little bit that you've got to memorize, then we've got the rules, right? So there's actual like vocab you have to memorize, then there are rules you have to memorize, and then you have to be able to manipulate those rules based on every different scenario, right? And so there's a lot of work your brain has to be able to do, which it can't do effectively until you actually master that stuff, until it's actually tucked into your long-term memory, which means you've reviewed it enough and studied it enough that it becomes just a part of your core knowledge, right? Does that make sense, right? So I emphasize again, right? Practice, practice, practice. All right. Okay, and then that brings us to the actual introduction to Chapter 5, and the introduction is pretty simple, right? Where we just talk about the concept of sodium, right? So this is pure sodium. This is what it looks like as a metal, right? It oxidizes very quickly. It's very reactive, and it's very soft. Like there are videos online where you can cut it with a butter knife. It's so soft, right? But it is a metal, right? And it's very, very reactive, right? Because also, if you're bored and looking at YouTube, you can find videos of sodium and other group 1 metals reacting with water very, very vigorously, right? Explosively sometimes. And then here we have a sample of chlorine, right? Actual chlorine gas. And obviously, you guys should know, right, that chlorine gas is definitely a poison, right? So if you were to intake pure sodium or pure chlorine, right, you would not fare well, right? But when we combine them, when they chemically combine, right, that's the key because that's what differentiates mixtures from compounds. When they chemically combine and they exchange electrons, they become a new compound, right? And this new compound, sodium chloride, right, is not only delicious, but necessary for our survival, right? Where there's a certain amount of ion concentration we need to have in the blood. Otherwise, right, our systems shut down. And so that's the importance of differentiating between a mixture and a compound, right? Because in a compound, the chemical properties change, right? Whatever it was, it is not anymore, right? Sodium chloride does not have the properties of pure sodium. It does not have the properties of pure chlorine. It is its own unique substance, yeah? All right. Then moving along, right, the law of constant composition from 5.2, right, tells you that in a compound, the composition is constant, right? That's basically what it means, right? As in the ratio of hydrogen to oxygen, right? Oh, that's not the one. The ratio of hydrogen to oxygen in water is fixed, yes? As in water is always 2 hydrogen atoms to every 1 oxygen atom, right? Always, right? It doesn't change, okay? What that means, right, is that the properties of water are fixed, yes? If the composition of atoms is fixed, right, then the properties are fixed, as in water that you get from the tap versus water that you get from a lake versus water that you get, wherever, right? All of it has the same properties of water, right? Same boiling point, same melting point, same conductivity, same density, same all those things, right? Because it's H2O, right? Whereas if we were to have a mixture, right, and the whole point of a mixture is that the composition is variable, right? The ratio of hydrogen to oxygen varies depending on how the mixture is composed, right? Which means that the properties also vary depending on the mixture, right? Which means that it's always going to behave differently, right? Depending on how you set that up, okay? Then we need to make sure that we understand the information conveyed by a chemical formula, because obviously that's going to be a big part of what we're talking about. So when we say Fe2O3, right, obviously this 2 is talking about the thing it sits next to. 3 is talking about the thing it sits next to. So what that formula says is that there are 2 irons for every 3 oxygens, right? So we could say that there are 2 atoms or ions. We'll clear that up in a little bit. We'll just say atoms for now. 2 atoms of Fe, right? And there are 3 atoms of oxygen, right? And this makes up 1 Fe2O3. Yes, like that's what that formula says, right? So instead of saying this, right, we could just say 2 to 3 is the ratio. Yes. Likewise, right, there's a mass relationship there, right? So for 2 atoms have a mass of 55.85. We'll say AMUs for now, right? to every 3 times 16 AMU, right? And there's a mass ratio that exists there, right? So going back to your book where it talks about how the mass ratio is not necessarily a whole number, that's because the masses of your individual atoms are not whole numbers, right? And if the masses of your atoms aren't whole numbers, then, that can't work. But the principle still remains, right, that we're still incorporating these relationships, yeah? Does that make sense, right? These two things say the same thing. One says it in particles, one says it in mass. We'll work with that a lot more later. All right. Thank you for listening. Be good. Stay tuned in the next one for where we get started with the actual writing of chemical formulas.